Okay, so we are starting a new chapter, chapter 2.1, derivative in the tangent line. This will be the first set of homeworks and assessment that will go into your second 9 weeks. All right, so we're going to start with something called the derivative in the tangent line. We've talked about tangents before. They intersect a curve in exactly one place, but we're going to go a little deeper with that. So definition of a tangent line with a slope of m. If f is defined, the function is defined on an open interval containing c. Okay, that means it exists everywhere within there. And it has this limit as delta x approaches 0 of delta y over delta x. If you recall, change in y over change in x, that is our slope, standard from Algebra 1. But we're trying to make that delta x, the distance between the x values on bottom, we're trying to make them go to 0 as close together as possible. Okay, that's equivalent to f of c plus delta x minus f of c all over delta x. That actually should look a little bit familiar when we were doing composition of functions. We did something like that, maybe with an h instead of delta x. We just didn't take the limit of it necessarily. That'll be equal to our slope of our tangent line. And so the picture on the right that has these, if you look, our 2 points are far away. There's our delta x, and we're going to gradually make them closer to closer. So this is a secant line. By definition, a secant line crosses in 2 places, and the closer and closer that those get together, so close in fact that there is no change in x and there is no change in y, that becomes our tangent line. So that's why when we do this, we do our limit as delta x approaches 0, as we are taking that distance and making it infinitesimally close. Okay, so we'll do some examples with the slope. So we're finding the slope of the graph of f of x equals 2x minus 3 when c equals 2. So it's asking for the slope at a specific location. It's asking for you to use that slope of a tangent line formula. So we are going to use this. This section here is called the difference quotient. Okay, so we're going to do the limit as delta x approaches 0 of f of x plus delta x minus f of x all over delta x. That's exactly what they gave us before. But the c is your constant, so we're going to replace the x's with our c value. Okay, so we're going to do the limit as delta x approaches 0 of f of 2 plus delta x minus f of 2 all over delta x. Okay, so then we need to simplify this. The limit has to stay following all the way through until we actually go plug in 0 for delta x. So this is just composition of functions. That means everywhere there's an x, I plug in what's in my f of. Okay, so in the first one, it's going to be 2, but instead of x, I'm going to have 2 plus delta x minus 3. Minus, parenthesis here is really important because you want to make sure you subtract the whole f of 2. And then instead of 2 times x, I'm going to have 2 times 2 minus 3. Again, that parenthesis is important that you subtract the whole thing, all over delta x, equals limit as delta x approaches 0. You may get annoyed rewriting that, but it is important. We're just going to simplify here so that when we simplify this, we will get 4 plus 2 delta x minus 3, and then 4 minus 3 is 1, so minus 1. I can simplify this whole thing as I go. All over delta x. If you notice, this here is minus 4, and minus 4 with 4 cancels, so I'm left with just the limit as delta x approaches 0 of 2 delta x over delta x. So the slope of the tangent line at the value 2 is 2. Okay, so it's a lot of algebra. All right, we're going to find the slopes of tangent lines. We're going to find more than one slope to the graph of f of x equals x squared plus 1. So since I have to plug it in for this c value or x value and this, I don't want to have to do what we did above twice. So I'll just leave x plus delta x as x plus delta x. And then at the very end, everywhere there's an x, I can plug in 0, and then I can plug in negative 1. So I'm going to do the limit as delta x approaches 0 of f of x plus delta x minus f of x all over delta x. That's your change or difference quotient. And I'm going to now plug in to this function. So everywhere there's an x, I'm going to replace it with what is in my f of. Keeping that limit as delta x approaches 0, I will have, instead of x squared, I will have x plus delta x all squared plus 1 minus the quantity. Well, I'm plugging in x and plus x, so nothing has to change, so I'll just keep it as is. That all over delta x. Now, where most people miss this is you actually have to FOIL that x plus delta x squared. So I'm going to, when I see this thing here, I'm going to think of that as x plus delta x times x plus delta x. That's what it means to square. Common mistake is squaring the first and squaring the last. So when I square that, I get x squared plus 2 delta x plus delta x all squared. Okay, plus 1. And then minus x squared minus 1. All I did was distribute that minus all over delta x. Okay, we can simplify. I got x squared and a negative x squared, and I got a 1 and a negative 1, and I now have the limit as delta x approaches 0 of, and I'm going to factor delta x out of what's left in the top so that I just have this. Oh, there should be an x here. Okay. Squeeze that in there. Okay. All over delta x. So that happens. You don't technically have to write that step. If you can factor and cancel without writing that step, that's okay. So now I am left with the limit as delta x approaches 0 of 2x plus delta x. In a fashion of our last chapter, to take the limit, I just go plug in whatever my limit is approaching. My limit is approaching delta x approaches 0. So I just am left with 2x, which is helpful because now at the ordered pair 0, 1, since there's not a y value, I'll just plug in the 0. I'll do 2 times 0, and I get 0. And at negative 1, 2, again, there's not a y, so I'll just plug in the x. If there was a y, you'd also have to plug in the 2, and I get negative 2. Okay. Otherwise, you would have had to do that previous thing twice. So the formal definition of a derivative, now derivative is a brand new concept to us, is of f of x is f prime. This is read f prime, if I can write, of x. That's how you would read this, f prime of x. Okay. It's not like a first power or anything like that. It's f prime of x. That means the first derivative of function is equal to the limit as delta x approaches 0 of f of x plus delta x minus f of x over delta x, which if you notice, that's the same thing as slope, which of our tangent, which is what we did previously. So those are exactly the same thing, but it's asking for two separate things. The wording is separate, okay? So the derivative is the slope of a tangent. So if you're ever asked for a slope of a tangent, you can find the derivative, okay? This is a definition of the derivative. So if you're ever asked to do the definition of the derivative, you have to do this limit as delta x approaches 0 of that difference quotient. Okay, so we are going to find the derivative of this by using the definition of the derivative. So we're not at a given location, which means we most likely will have a variable in our answer. So doing the same thing, limit as delta x approaches 0. Our definition of the derivative says that we will get this f prime of x equals, while we're getting ready to do, f of x plus delta x minus f of x all over delta x. Okay, so f of x plus delta x, in place of my x's, I'm going to plug in what my f of says. So I will have, instead of x cubed, I'll have x plus delta x cubed. Plus 2, instead of x, I'll have x plus delta x. Okay, then minus that whole thing. Again, I'm using parentheses to make sure I subtract that entire thing over delta x. And I forgot something really important. Hopefully, if we were on class, you would remind me. Okay, limit as x approaches 0. Delta x approaches 0 equals. Okay, so I'm going to keep my limit as delta x approaches 0. Now, keep in mind, kind of like we did before, instead of cubing or squaring something, we're going to do x plus delta x times itself 3 times. Okay, so you'd have to do x plus delta x times x plus delta x times x plus delta x and carefully distribute accordingly. And when you do that, you're going to get x cubed plus 3 x squared delta x plus 3 x delta x squared plus delta x all cubed minus x cubed minus 2x. I distribute that negative all over. Oh, I left something off, didn't I? Eraser. Okay. I almost forgot to distribute this here. Minus 2x, or plus 2x, plus 2 delta x, and then my minus x cubed minus 2x. All right, all over delta x. So really, really long, but it's not as bad as it looks because negative x cubed and x cubed. And then I have 2x and negative 2x. And then I have, I'm going to rewrite this just so I can see it better. I do apologize. My handwriting is not the best. And so I have 3x squared delta x plus 3x delta x all squared plus delta x all cubed plus 2 delta x. So then what I'm going to do is, since we're dividing by delta x, again, you could do that step that we did before where I factored out a delta x and then I canceled in the bottom, or you can do that in your head. So I'm going to cancel one delta x out of everything. So this delta x is gone. One of these is gone. One of these is gone. And that's gone. All right, so I am left with 3x squared plus 3x delta x plus delta x all cubed, not cubed, but squared because I took one away, and then plus 2. So it kind of squeezes it, and that delta x on the bottom is gone. So now what I can do is I can drop my limit because I'm going to go plug in 0 everywhere there's delta x. So this will become 0, this will become 0, and I will be left with 3x squared plus 2 because that whole thing comes 0 because multiply 0. And that is the derivative. What'll be fun is later on you will learn a shortcut for this. So anytime you ask for the definition of the derivative, you have to do this long way, but you will have a short way that you can check it. All right, find f prime of x. That means asking for the first derivative for f of x equals root x. Then find the slopes of the graph of f at 1, 1, 4, 2, and then discuss the behavior of f at 0, 0. So there's a lot in this problem. Again, when it says find the slopes, it is asking for the slope of the tangent line, and the slope of a tangent line is the same as f prime of x. Okay, so no big deal there. So what we will do is we will do f prime of x equals the limit as delta x approaches 0 of f of x plus delta x. You don't have to write this thing every time, but I do think until you have it properly memorized, it helps so that you can see what you're plugging into. So in place of x, I will be putting x plus delta x first, and then it'll be itself. So I will have the square root instead of x. I'll have x plus delta x minus root x all over delta x. So I have this, which is crazy looking. So the problem with it is I can't plug in 0 as is because it's undefined on the bottom. That's why you have to do so much manipulation. So what I'm going to do is I'm going to multiply, kind of like we did a couple sections ago. I'm going to multiply top and bottom by the conjugate. So x plus delta x plus x instead of minus. What I do to the top, I have to do to the bottom. Reason I do that is because now when I FOIL out the top, it'll help cancel some of the things out, and it's okay to have some of those things in the bottom. Okay, so my top, when I do my first, I'll have the same thing in a root, but it's squared, so I'm just going to have x plus delta x because the root will cancel because it's squared. And then outer, I'm going to have root x times root x plus delta x, and then I'm going to have minus root x times root x plus delta x. So those will cancel, and then I'll be left with minus root x squared, which is just x. So the top becomes really, really nice. The bottom, do not distribute this If you do, you're going to end up having to factor it to help you out. So it's just easier if you don't. So we'll leave it like that. All right, so the top is nice, and I have those canceled. And I also can cancel out that because top and bottom have it entirely. With those x's gone and canceled out, then there's just a delta x, leaving a 1 on top. That's where most people miss that. Root x plus delta x plus x. So that now I can go plug in 0. Okay, leaving me with 1 over 2 root x. So that is my f prime of x, which is actually this equation for my slope. It's not the equation of my line, it's the equation of my curve, it's the equation of my slope of my tangent line to my curve. All right, so then we will do m equals something at, so we'll do at 1, 1 first, and my slope will be equal to, plug in 1, 1. Well, there's not a y value, there's just the x value, so 2 root 1, which is 1/2, one of my answers, at 4, 2. My slope is equal to 2 over root 4, with a 2 in front of it here, and that'll be, root 4 is 2, so we'll have 2 over, or that's a 1 over 4. Okay, and then it says discuss the behavior of f at 0, 0. So let's kind of look at that. So at 0, 0, my slope is equal to 1 over 2 root 0, which is undefined. What kind of lines have undefined slopes? Okay, if you think of that in a graph, if I graph something as undefined slope, it is a vertical line. And so you can actually say that the slope has a the slope is undefined. So f has a vertical tangent. If it had been 0, you could say a horizontal tangent. Okay, so it's just wanting you to describe that. All right, last example, and then we have one thing to discuss. We are going to find the derivative with respect to t for y equals 2 over t, and then we're going to find the equation of a tangent line. So we're actually going to write an equation like y equals mx plus b, or y minus y equals mx minus x, like we did in chapter P. So first, though, we need to find the slope. You can't write the equation of a line without a slope. All right, so my slope of my line is equal to my f prime of x, which is the limit as delta x approaches 0 of f of x plus delta x minus f of x all over delta x equal to, all right, and then everywhere there's a t, I'm going to be plugging in what is in my f of's. Okay, so in place of t, I'm going to have x plus delta x, and in place of my t here, I'm going to just have x all over delta x. Problem with this is I really do need to combine those fractions as they are, so I'm going to have to get a common denominator. They just are going to multiply by each other, so I'm going to multiply top and bottom of this by x plus delta x. If you do the top, you have to do the bottom, and over here I'm just going to multiply by just x. Okay, and then I'll rewrite it. Limit as delta x approaches 0 of 2x minus, I'm going to distribute 2 delta x minus 2x. I distribute both that negative and that 2 all over, and they have a common denominator of x plus delta x times x. Okay, and then don't forget the delta x here on bottom. Okay, you could write the whole thing over delta x, but then if you were to divide a fraction by a fraction, you're multiplying by the reciprocal, you can also put that delta x here in the denominator. Okay, it's where it's going to end up. All right, so then what I can do is I have a 2x minus a 2x, and then I have the limit as delta x approaches 0 of negative 2x to delta x all over x times x plus delta x times another delta x, and there's a delta x multiplied in the top and a delta x multiplied in the bottom. So those cancel, and now I can plug in 0. Before then I couldn't plug in 0 because it would be undefined. So this becomes 0, and I'm left with negative 2x squared. Okay, so that is my derivative. Okay, except you would put t in place of it, but that is my derivative. Then we're going to find the equation of a tangent line. Okay, so my slope is equal to, we're looking at the order pair 1, 2, is equal to that order pair plugged in. So negative 2 over 1 squared, which is just going to be negative 2. And then if you remember, we have y minus y1 equals m x minus x1 from algebra 1. We can write the equation of a line that way, or you can put it in slope-intercept form. This way would be simpler. So I'm going to do y minus my y value from the ordered pair equals my slope that I calculated, x minus my x value from my ordered pair. You can leave it like that, or you can distribute and simplify and write it in slope-intercept form and get y equals negative 2x plus 4. And that would be okay too. So this or this would be acceptable. Last concept is just the concept of continuity that we talked about before, like a function is continuous. Remember, you don't pick up a pencil if you're tracing it and whatnot. It's differentiable. If it is differentiable at certain values, and it's continuous at that value. So you could actually test differentiability by seeing if you can, if it's continuous throughout it. And so sometimes that'll help you. If you're not sure if you can take the derivative of it, you might look at the graph and see if it's differentiable where it's asking you at. All right, be looking for that homework and make sure you keep up with things so that this next quarter can go a lot more smoothly. 3 weeks from today, I will be back, and I look forward to seeing you all. All right, talk to you soon. Bye.